Okay, so this is my goal. I want to convince you that the centripetal acceleration is b squared over r. And remember, is this a vector or is this a scalar? It's a scalar equation because this tells you the magnitude. If this is out of the glare, yeah. So this tells you the magnitude of the centripetal acceleration and the speed, right? The velocity. So it's all magnitude over here. Okay, so be careful. The direction is taken care of separately. It's not in the equation. The direction is separate. Direction is towards the center. Okay, that's taken care of separately, right? So I'm talking about acceleration and the magnitude and direction separately. Okay, so first to find the acceleration, we want to start with the position. Okay, so remember the formal approach is, let's draw this out, right? So I will use this as the center and find out, hey, this is an object that is going to move around in a circle like this. What is the position? Well, that is the position r. Okay, so the position as a function of time is what? Well, that's theta. So I can draw this down over here, right? And over here and find out its components. What is the x component? Well, the x component is the distance of this times cosine, right? So this is the x component, and this is the y component of r, and the magnitude of this is exactly the radius. And so now you see why we call it r. It's exactly the radius. So it's r times cosine theta and r times sine theta. So that's the x, that's the y. Now, if this goes in a circle, theta actually changes as a function of time, right? But how does theta change as a function of time? Well, so the question is, right, how does theta change as a function of time? Remember, we introduced the idea of angular velocity, which is supposed to be delta theta, d theta dt. It's the rate of change of theta with respect to time. But because we are interested in the case where this is constant, then it's the same as this. Right? Same as delta. Now, what is delta? Well, over here, we are going to set this as 0. So delta naught, we're going to use the polar angle, whatever it starts as 0. And so this is theta minus theta naught over t minus t naught. But we'll set our starting time and starting angle as 0. So it's just where you're going to decide your it's basically where you're going to decide x equals to 0, where you're going to decide theta equals to 0, where you're going to decide time equals 0. You want to set your origins. So we're going to set the x equals 0 here, y equals 0 here, theta equals to 0 as this part, so the polar angle definition, and time equals 0 to whatever the starting time of this is. So the omega here simplifies to theta t, right? So theta as a function of time is just equals to omega times t. That makes sense because you can plot this out. You can draw what theta against time. Right? What is omega t? How does that look like? That just looks like a straight line. So that means at every single time, the theta is included. So T1, T2, T3, T4, right? At every second, theta just increases like as in a constant slope. So theta at every second, theta just increases at a constant rate. Okay, so that's basically uniform circular motion. Okay, so I can write r cosine omega t and r sine omega t. That's r. So what's velocity? Well, velocity as a function of time is the rate of change with respect to time of the position, right? It's how much the position changed with respect to time. So what we can do is, again, it's better for presentation to write it vertically, unlike what I did over there. We do ddt of r cosine omega t, because that's how theta changes with time. Omega t, that's how theta changes with time. It's omega t, r sine omega t. Okay. Now, this is a scalar operator. It's what's called a scalar operator. It's basically like a scalar, and it's an operator. So you can operate on the x and y components separately. So you can do this, but the r is a constant. Why is the r a constant? It's a circular motion. So the radius is a constant. That's a definition of a circle, right? So you have, you ignore r and differentiate cosine, which is minus sine of omega t. But you have a constant, right? So you need to pull that out, omega. And you differentiate this again. So it's r, and this will be cosine omega t, right? Change sine to cosine, but you have an omega, so throw that out, right? Use the rule that I just erased. And yeah, that's it. So let me just rewrite this a little bit nicer. So minus r omega sine omega t, r omega cosine omega t. Okay. That's the velocity. And finally, let's find the acceleration as well, because I want to find the acceleration. Okay, so the acceleration is ddt of velocity, the rate of change of velocity. So this time we'll do it quicker. So I'll just write this as minus r omega sine omega t, r omega cosine omega t. And differentiating that, these are constants, right? The omega is constant because it's a constant speed, constant angular speed around the circle, and a constant radius. So I just have to differentiate that, which gives me minus r omega cosine omega t. And I need to throw out one more cosine, so the cosine square, and I need to change that to minus sine omega t, and throw out an extra omega, and that's what I get. All right, so what have we achieved so far? So I found the position function, right? I know exactly at every single time, what is the position of this object. I know at every single time what's the velocity with this vector function over here, and at every time what's the acceleration. Now, what's the direction over here, and how can I I'm curious about the magnitude, right? How do I find the magnitude? Well, the magnitude is well, first of all, let's pull this part out, because I have some common factors over here, and I realize in fact I'll just pull out the omega like this, and I'm left with r cos omega t and r sine omega t. Do you recognize this part? Well, you look over here and then you see that same thing. So what do we have? We have minus omega r, omega square of r. Okay. So that's important. Why? Because that's a constant, but there's a negative, right? Let's emphasize that negative here. It means wherever r is, a is always negative of r. So r is the vector that goes from the origin to the object, and a will always be pointing back to the center. Okay, so I've proved to you the direction. Okay, so now how about the magnitude? Well, let's take the magnitude of this. So the magnitude on both sides. So I've proved it I'm halfway done, right? I've shown that the direction is always pointing towards the center, no matter where r is. These are all functions of time, right? So at any function of time, a is always pointing to the center from this result. All I did was find out r as it goes around the circle and take two derivatives, and I realized this is a fact of life, that if you go in circular motion, a is always pointing towards the center. How about the magnitude? The magnitude is well, you take an absolute value on both sides. So you just have this, the absolute value. You can take the absolute value of each thing individually. Minus sign just goes away. The absolute value of omega square is just omega square, and now you just have to absolute value of r, like that. The lazy way of writing this is this, right? So there's a difference between the vector form. There's a minus. This doesn't, because this is looking at the magnitude of a and r. Okay. This is actually an important formula, but it's not the same one we have. Can we get rid of the omega because we're not that comfortable with it? Let's replace it with something we're more comfortable. Well, omega is how much angle it travels with how much time, and it's a constant. We know that the angular velocity, right? The how much angle it travels per unit time, it's going to be constant. That's our definition of uniform circular motion. Now, if I've traveled 2 pi, right, in radians, if I travel 2 pi, how much time does it take to travel 2 pi of angle? It takes 1 period, right? So 2 pi over t, okay? So that's that. And if you remember before, if I look at a linear velocity, let's try to piece everything together. The linear velocity is how much distance per time. So if it travels 2 pi r, it takes, how long does it take? It takes 1 period of time, right? That's the distance it travels. That's the time it takes. That's the linear velocity. That's the angular velocity. That's how much angle it travels, and that's how much time it takes. Can I relate the two? Well, yeah. Yes, you can see this is just omega times r. Okay. Again, this is a formula that only works for circular motion. All right, so what if I square both sides? I square both sides. I have v squared equals to, should I write it on over here? Yeah, let me write it over here. So if I square both sides, I have v squared equals to omega square r square, like this. And that means omega square, right, it's v square over r square. If I plug this back into the a, right, a is v square over r square times r. And you can see the magnitude over here is v square over r. Okay, so for circular motions, if you like, you have you have one additional formula over here. That is, this is, and also the second one, this is about the magnitude. This is about the full vector relation. Okay, so this is really for completeness to show you where this comes from. So it's really from the formal approach, you can see the power of that. If you if you're able to describe the position at every single point in time, you can figure out all the relationships that there is. But the important thing for you to be able to do is to be able to utilize these facts. And of course, centripetal force is mv squared over r to solve the problems. You will not be directly examined on the derivation of this, but for completeness of the course, because you're here to learn where things come from, hopefully, and you now see that there's nothing really genuinely new. It's really applying everything you know in kinematics, that the fact that the velocity is the derivative of position and the acceleration derivative of velocity to figure these things out, okay? Also, you will see very little about differentiating trigonometry in this course, but in 3C, you'll see a lot of it. So hopefully by introducing this now, it's not directly examinable, but you've seen it once or twice, and it will become more easy for you when you finally get to 3C. Okay, all right, so that wraps up circular motions. Remember the most important formulas there, and also some of the definitions we introduced. Do a couple of problems, you'll see that's not that difficult, and we'll see you in the next lecture about universal gravitation, which wraps up everything about forces and motion so far.